Yeah, no, 36 was the one that crashes. It's doing its stuff.
Okay.
Is Maxime not around?
There.
Yes. Completely crashed. Went well until slide 36 and then everything crashed and some crashing.
And let's keep like that.
What? Okay. Is it based on the 36?
Yeah.
Because if it's always on the same, maybe you can just
That's why I
skip
said
to skip to the
let's
next
keep
one.
it. Yeah, like if we can start on this one.
Starting this one. Okay, I will try. So that's
Maybe it's excessive because it's on the USB drive.
I cannot share without the screen. And just go on the computer as
It's totally normal.
Oh, it's not my computer. Just so you know, it's not my own computer. But somehow it wouldn't be able to connect. So, yeah.
Um, Let me try again. Not from the USB drive. No.
just with the small screen and that's those. No, with the clear screen.
Computer is fed up at the end of the day. Too many short talks.
It
Of
was
course.
information.
Yes, was too much.
Maybe because we learned too much, the CPU is 4 now.
Yes.
Yeah, we tried the last time. If normally ask me if here is the problem for the we want to share the PowerPoint with the full screen. It didn't work for the computer, so maybe we will try to present with a small screen. But yeah.
Okay.
So you don't have the 37?
You know?
You want me to go with the 37
Yeah.
with the small screen? Okay.
Oh.
So we go
Yes.
just this one like this, and
Okay.
on the 38 I will
Sure.
go back to
Okay.
need the videos.
Yeah, there is one video there. So, okay. Okay, then, so one of the things that we did was actually with a targeted microbubble to see if you can also induce drug delivery with that. Because that was not known back in 2011. So what we did is use the Banderas, but then there was a very standard microscope on it. So you could only look in really with one fluorophore. So we chose for propionimidite. So before the ultrasound, you didn't see anything. It was completely black. But this was the on the bright field, so there were 3 endothelial cells lying there. And after, so then the microbubble was oscillating, that was recorded. And this recording then resulted in the local, membrane poration, and therefore also the uptake of propydium Yes, and then you can go to the slide 38 again, but then on the big screen, right, with a different one. Yes, thank you very much. Yes, and then we also started to look at, okay, what about the differences in the like the diameter of the bubbles during these oscillations? So we took the maximum and minimum divided by the resting radius, and then this is the initial radius of the bubbles, and then we just looked for this 1 megahertz, and there was yes. It is, yes, yeah, definitely. So what we did, it's a targeted bubble to CD31, which you can use in vitro. And then the cells were like this, and the bubble was on top. Therefore, we also knew that it was targeted, because otherwise bubbles will float up. And this was really there. So it was really bound to that cell. Yeah. And this was 80 kilopascal. We thought, okay, maybe we need a little bit higher. So we went to 120 and was like, well, let's go even higher. And then we also saw some more sonoporation or PI uptake. You also see, of course, a lot of difference between bubbles of the same size. So this was with the old direct bubbles still. And there's a threshold, so which you need to go above to get your sonoporation. We also looked into, does it matter where this bubble is on the cell? It's different locations, and there was not really a difference. You could or could not get sonoporation. Okay, there was not on this one, but maybe if the N would have been higher, this would have been the case. So not long after, there were people that were using a confocal microscope to actually look at what is happening to a cell that has a bubble on it. And this was from the Alfred Yu, his group, and it was published in 2013. If I start a movie, yes. Oh, do you see that? So this was the very, very first time that anyone witnessed a really live sonoporation event. So we'll go again. It was on a fibroblast. So here, and then you have a pore in the membrane, and then it closes again. I can still look at this movie for hours. It was amazing, beautiful. It was really the first one that was able to really prove this, because no one else could do that before. Not long after, there was also a publication in 2016 that showed other effects. So this was on endothelial cells, and then you also see things happening here in the membrane. So you also get black, meaning that it's opened up. And there was also propydium uptake at the same time. Here were more channels. So yeah, this is all very beautiful, but at the same time, we can't see the bubbles in here because there's no ultra-high-speed imaging that was performed. So we have no idea what the correlation is, what kind of behavior the bubble did. So, but what we do know is that from these studies, we know, okay, there's definitely pore formation, and there can also be opening of the cell-cell junctions, because maybe if I go back just one more. So actually over here, that also means that there's an opening between the endothelial cells, and you see also here it occurring. So somehow this sonoporation event also opened up the cell-cell contacts. So we know, okay, those two mechanisms are clearly there. But yeah, is it the bubble that directly does the opening? We don't know. So what if we could have a setup that on the one hand, has not just a microsecond resolution, but also the micrometer resolution, that has it both? Well, if we then have, for example, the Branderis and a confocal microscope, that would be really great. And that's what we set out to do. So this is the confocal microscope that was custom made for us. It's coupled to Branderis to result in this. This is the optical imaging system. And with that, we started to investigate the correlation between everything. So here's an example. So this is before the ultrasound. You have your bubble over here. So nuclei in blue, in green, cell membrane. Then you switch to the ultra-high-speed imaging for the microbubble oscillation. You can determine the radius versus time. And then this is after the ultrasound. So you get local uptake of the propylium iodide, and this is the movie of that. Now that is one example. I also have another one. Here the bubble oscillates again. Radius time curve here. Quite soon after, you see propylium iodide uptake, but look also over here. I mean, there were already a little bit of like black spots here, meaning that the cell-cell contacts were not completely intact beforehand, but then you also see that those start to really enhance. And even at another location over there. So this is the movie of that. And then we could start to investigate if there's a bubble oscillation that you can correlate to a certain feature. Yes.
I was wondering on slide 46, is that just the one bubble? Are there no bubbles near the?
There's no bubble near there. Yeah. That's because otherwise it will be really difficult to investigate what is caused by one bubble or what is caused by the other. You have interactions between the two. So these were all single bubble studies. There's only one there. Yeah, correct. Yeah.
And the effects happening at that part is.
Yeah, the bubble is here, and I mean, those distances. That's what it's happening at. Yes, but it's like 15 micrometers, 20, 30 micrometers away. So it's not that big. Yeah, indeed. Yeah, and what we found is indeed if you have no effect or there is an effect like sun operation, there is indeed like a significant difference. There was already also a little bit of cells that could just retract without any sun operation. But like we couldn't really see if there was an operation and retraction. We didn't really see significant difference in bubble behavior between the two, suggesting there was not really a bubble-specific phenomenon going on there. We did look at the bubble location because maybe that also was causing it. Maybe if a bubble is very close to a cell edge or far away, I mean very close, maybe then also the cell-cell contact opening will be better. But that was really not the case. So here everything was not significantly different. So that in a way is good because in vivo you will not be able to place a bubble on a certain location on the cell. It will just happen somewhere. So in that respect, it's good. But yeah, so for this, basically this, if we go back to pathways again, it made us realize that the microbubble oscillation itself is not the one that is causing the cell-cell contact opening. So what is? There had been lots of studies looking into calcium, like that the calcium is increased upon ultrasound and microbubble. So then we thought, okay, what about if we look at that? So we added a calcium dye, and that's pseudo-colored here in white. The microbubble was on this location. And oscillation. And then this is what happened. And then you see a huge increase of the white, meaning that there's really a calcium influx going in. And in this case, it also went down again. So quick up, down, and you also see going up in all other cells, the surrounding cells. So meaning that even if you just sonoprate one cell and there the calcium goes up, this calcium is a wave that is going through the other cells as well. Now, also brought another example. Oscillation again, and then this. So it went up. The calcium also caused a wave, but here it just stayed up. So it didn't diminish during these recordings. So it was always propylium iodide too, but It's a little bit difficult to see with all these colors on top, but I hope you can appreciate that there's red in there. And there was another one I want to show you. So again, single bubble, oscillation, and then this is what happened. So what you actually get is not, you get a high, your first, it will play again a very high amount of calcium in the cell, like here. And then it diminishes, but it goes into these clusters. You get these clusters into the cell. You get, there's also a lot of black going on over here. So this whole cell just retracts and diminishes to a very small thing. And yeah, that's indeed at those locations. So, and then we started to look at the microbubble and also the intercellular calcium correlation. And then we saw that there's actually 4 things going on. You can either have just stable calcium, there's going up and then down within 180 seconds. It's going up and not going down for at least 180 seconds, and there's these clusters. Now, and there we saw that there is a significant difference for everything in terms of the microbubble oscillation. So hey, there is a correlation. And also, if we looked into actually what is going on between sun operation and no sun operation, well, if there's no sun operation, calcium is always stable. If there is sun operation, there can be a variety of these calcium influx. And why is calcium going in? Well, calcium outside is always 1,000 times higher than what's inside into the cell. So if you create a tiny pore, there's always an influx of calcium from the outside to the inside. So that's why it's an increase. Now, we also looked into more about the cell-cell contact opening. And there we saw that if you have a cluster in calcium, 80% of was actually causing the cell-cell contact opening, and a lot less for the others, suggesting that these 2 are really the main ones that you need to somehow induce to get your cell-cell contact opening. Well, we can go back to this mechanism again. That was not the case, not directly, but if there's calcium that will normally go in by a pore, then that calcium somehow signals in the cell and says, open up your cell-cell contacts. Now, and that also actually showed that these 2 are not independent pathways, because the sun operation is actually needed to get your opening of your cell-cell contacts. So it's not an independent thing. And is that all? Well, no, there are also other types of things out there. There's the cell membrane effects called blabbing. This is again from the group from Alfred Yu, where you can see that like beforehand, like it was very smooth, but then after the ultrasound, you see really this blab forming. And that also was the location where was the propydium iodide going in. And that is what was thought. So here is more like the blab diameter also versus the PI relative intensity. So the higher the blab, also the more like the bigger the blab, also the more PI. And there was also a relationship between the blab lifetime. So if there was more propydium iodide in the cell, there was also a longer existence of this blab. Well, why is this going on? Well, there's still a little bit of a question out there, but it could be an injury control mechanism, because you do make a tiny injury, of course, to that cell when you create a pore, and then this is an injury control mechanism. So this is interesting and still needs further investigation. What we also were actually doing is looking at different types of microbubbles. So you have your non-targeted one, and you have different ligands, so alpha V beta 3, CD31, or an IgG kappa 1. So that is an isotype control, which will not bind. So for this, we did also the different configurations. So under the cell, because that's the only way you can investigate a non-targeted bubble, And for the isotype control, you can also do that. But for really targeted ones, you can also turn the cells to be at the bottom, and then your bubble is on top. And then we investigated with our ultra high speed and confocal image by doing actually Z-stacks. So looking three-dimensionally, do confocal microscopy, and then during that time lapse, do an ultra high speed image, and then do another Z-stack again afterwards. And this is what we actually saw. So this is like slices through those 3D recordings. And for the non-target microbubbles, there it's easier to look at this plane. Those were always underneath the cell, including for the isotype control ones. But then look at this one. This was an alpha feedback. The 3 target bubbles was completely inside the cell. It didn't matter which configuration. For the CD31 target bubble, it was partly in, and not so much when it was on top. And these are just single examples, but this was also quantified. And if you then look, then indeed these bubbles were completely internalized. And it was like, okay, if a target bubble is being internalized by an endothelial cell, what will that do for drug delivery? Can you still use that? Because what we definitely saw is that when a bubble is internalized, the excursion amplitude is lower, which makes sense because the bubble has more difficulty to oscillate when it's inside a cell. And this was also basically determined in bins, because here you cannot really do statistics on it because it's so much of a cloud. But if you bin the bubbles, then you can do statistics. And for up to 3.2 radius, there was a significant difference between bubbles that were internalized and not, in terms of their response to the acoustics. Now, what about the drug delivery? This is an example for a non-targeted bubble. And for the 3D imaging, we take a smaller area because then otherwise it would take too long. So this is what it looks like. And then you see a smooth membrane to start off with. That is the bubble. And then that bubble is insonified, like so. Radius time curve. And this is what happens for the cellular response. So propylium iodide uptake, because cells becomes red, and you do see a pore formation, but there's also still a little bit of green really on the bottom part of the cell. So this is just the apical membrane that you perforate. And we'll play again. Okay, and you also see here the cell-cell contact opening actually. Now, this is still images. So here the pore starts to create and becomes bigger, and you also see the propylium iodide going up. And this is afterwards. And here is a bleb, just like Alfred Yu groups showed. There is also the cell-cell contact opening, and there's still at the basal lateral side a membrane visible. We also had other observations. So it's again a non-targeted bubble, insonified, radius time curve, and then here. And here, this bubble, actually, if you look at the black here, it's completely black. There's not really any green on the bottom side, so it's really through and through. And that is hopefully also appreciated in the still image. So here, pore starts to create. And then also propylium iodide goes in, and we were wondering, like, what's going on? Is this really a pore? And if you then look at the 3D afterwards, it's actually a hole through and through. So both the apical and the basolateral membrane of the cell. And we started to call this a tunnel. And then we looked at occurrence for all these different bubbles, above and under also. And then we noticed that if a bubble is actually so these are the ones that are mostly internalized, then here you hardly see any tunnel formation. And that was actually the main one. And we also saw some cases that there was propylium iodide uptake for sure, but there was not really a visible pore. And that category was also mainly in the bubbles that were internalized. Now that is on that side, but what about the excursion amplitude of those bubbles and the thresholds as well? And then we noticed the difference between the different bubble types, because the threshold for sonoporation was 0.9, but here it was 0.7, and these were the bubbles that were most internalized. So they oscillated less, but somehow that didn't matter. They were still able, at this lower oscillation amplitudes, to induce either, like mainly the sonoporation. So therefore, in conclusion, 3D morphology can be very different, determined on the bubble type. And the duct delivery, you have an indistinguishable pore, distinguishable pore, a tunnel with low PI uptake, and that really just then closes the cell off. It's like a donut if you look at it in 3D, and you can also still have a donut with a high PI uptake. Now the internalized microbubbles they had a damped oscillation, but luckily also a lower threshold for the sonoporation. So that was good. So we can update this pathway again. We can add now tunnel formation to it. And that was indeed the bubble that was inducing that. Oh, yes, this should have. Okay. Then what about other cellular structures involved? Because there's lots more in the cell. And one thing is F-actin. And I'm not sure if everyone knows what F-actin is, so I'll briefly introduce. F-actin is actually, so actin has monomers, and if they form a filamentous form like this, linear strands, it's called F-actin, like in filamentous actin. And it's inside the cells as like a cytoskeleton, like cytoskeleton. So it's mainly, just below the membrane. And Alfred Hughes group investigated what was going on with the actin. So for the actin, if you want to visualize that, you need to genetically modify your cells. There's no live cell dye for that. And then on this strip, so this was a single cell on this strip, they looked at what's going on with the F-actin. And then after the ultrasound, they saw that it was gone at that location of the bubble. And then it slowly started to come back. And that was coinciding with the reversible sonoporation, and there was also PI uptake in that cell. So these were endothelial cells, and if they looked at the recovery time after of the F-actin, and also the receiving time of the cytoskeleton, that was really like a trend there. And also, if you look at the time after exposure, well, there was definitely also differences in the receiving time and the recovery time, also for small and large pores. So there was a lot going on with the F-actin with this sonoporation. And if you also then look at the closing time of the plasma membrane, well, versus the receiving time, then this lag behind. So you first get your plasma membrane that closes up, and thereafter your F-actin. So that's lagging behind. And this was done on single cells. But yeah, endothelial cells are not single cells. They're always in a monolayer. They're always attached to one another. And that made us start an investigation on F-actin ourselves. And we used a little bit of a different approach using a green fluorescent protein called LifeAct. And this LifeAct actually can attach to the F-actin without interfering with its function. So it's a little bit more of a gentle approach. And this is really very novel data. So it's not been published. First time ever showing this. Also, there was definitely bubble recordings here, but it's so new that I've not been able to incorporate that yet. So just look at the cellular response. So because you do transfections, it's not 100% that these endothelial cells get fluorescent. So it's definitely a monomer. You can see that from the cell membrane dye that we add. But here, not like there were 2 for sure, and also there were 4 cells there that were fluorescent, and the bubble is on this one. Now, if you then they all play together, but then look at this. So if this is the combined all 3 laser channels, there's rubidium iodide uptake because it becomes red, and it will play again. And maybe you can look at also what's going on in the channel. So it's a 4-minute movie, and then it will play again. So here, and then you get the ablation of your actin strand, and it's one of the main ones. And if you ablate that with the bubble oscillation, it just means that the cell is losing its tension and can only retract. So somehow this F-actin is actually doing something with the retraction that's causing the cell to retract. So we can add, oh, that, yes. So we can add that F-actin is likely causing the retraction. But I hope at one point to be able to, show you more on how and why. Now this is all in vitro, but yeah, I mean, a patient is not in vitro. So what about in vivo? In preclinical data, there's actually also, and this is the great research by Katrina Lange-Davies. So she's here in the audience. I hope I do your research proud by presenting it in front of you as well. So what they actually did is they used a mouse with a tumor, and then in this dorsal window model. So the tumor is inside, and then they place the mouse under the microscope. So they also have the stage here where they put it on. And then this is the ultrasound is also nicely coming from a 45-degree angle through the tissue. And then, so you'll be able to visualize things. And this is what they observed. So this is the nanoparticle stabilized microbubbles. And then at 0.8 MI. And then this is a small square that is then shown here. And then this is before. And then after the ultrasound, look at the extravasation. So in green, you're looking at the dextrane. So it really nicely extravasates. And you also see a lot of red appearing, meaning that those are the nanoparticles that you're seeing. And you also see this at a lower MI, a little bit less to the extent, but you definitely see that there too. Really beautiful. So what we're doing in vitro really does occur in vivo as well. You can get extravasation. And they also looked at more specifics, for example, the time until the extravasation. And interestingly, the MI does seem to play a role. And at 0.6, it was really, very shortly after. And also at 0.8, it was faster than for the lower ones. And there's also the Sonofew that they compared with. This is just a standard microbubble out there, so you can also do it with that. So it's beautiful, beautiful work. Now, that concludes the vascular delivery part. What about bacteria? Can we do something there? Well, we are actually covered in bacteria. I don't know if you all know that, but we are. And it's good that we are, because we need them to get our vitamins and also to digest our food. However, there are also bad ones out there that can make us really ill. Food poisoning. I hope we will not get that during the conference. A UTI, which lots of us have already experienced, I guess. Chronic wounds are not nice. And infective endocarditis. It's a bacterial infection on the heart. Please don't get that. Really, really bad. And yeah, then we were thinking, well, they can be on tissue infections, also medical devices, you know. Well, there are antibiotics out there, right? So why bother? Well, it's costing 1.1 billion euros per year. Well, but what's more actually worse is that it's projected that in 2050, the antimicrobial resistant infections will cause a lot more deaths than cancer will. So this is one to worry about. And then we thought, well, what can we do? Can we do something? Well, bacteria are not normal mammalian cells. You have gram-negative, you have gram-positive, and they have a very complex structure. So the gram-positive ones have a double a bilayer, just like mammalian cells, but they have this very thick peptidoglycan layer on top. So it's a very strong membrane. Now, the gram-negative ones actually have two layers of lipids outside, with then also a peptidoglycan layer in between. So this is a completely different membrane that you're looking at that you need to do something to. So yeah, examples of types of bacteria. They have different shapes as well. So also another thing to think about. Size is about 0.5 to 5 microns. So these are actually about the same size as our bubbles are. Now, can we do something there? Well, here again, you need to look at the interaction between everything. And can there be sonebration? Can there be something like dispersion? And this is what we call sonobactericide. So it's actually the use of ultrasound and cavitation nuclei with or without antibiotics and maybe other substances to treat bacterial infections. So let's take a look what can be done. So this is from more recent from my group. So these were the bubbles with the Staphylococcus aureus biofilm from a clinical isolate. Used the confocal microscope, different ultrasound settings to look at what is going on. So every green tiny dot you see in here, and there are about 7,000 to 8,000 of those in your field of view, that's one bacteria. And those are stained, so they're living. You also see some tiny red dots, so there are already a few dead ones in there, which is typical for a biofilm. And then in pink, you have the bubbles. These are non-target bubbles, and this is what happens if you turn on the ultrasound. So there's no ultra-high-speed imaging there, so you will see bubble movement, but not oscillation. And what we started to see is that in certain locations, you can get that you just wipe off your bacteria. So there's some dispersion going on. And also, there's some sonebration going on because over time, and this is not playing right, but over time, there should have been actually that there are red ones popping up. So different time scale too. What about if we increase the pressure to 400 kilopascal, so twice higher than the example I just showed? Well, then this is what happens. Pac-Man, you know the game? It's like you wipe it out. Well, great, get rid of the bacteria. But we're not sure if you actually kill them at the same time because they leave the field of view, you can't really see them, so there's a lot we still need to investigate. But this is completely different from what we've been seeing for endothelial cells. Or you can just put everything you know about endothelial cells. Yeah, it's useless. You have to start all over again. We also, of course, looked at the changes in the PI positive cells in the field of view, and yeah, then with microbubbles, and yeah, it was not really something that that you could really. Yeah, okay, there was at 400 kilopascal and 100 cycles. There was definitely change going on, but not really great. And if you added an antibiotic, well, not really any difference at that direct moment. So, but the dispersion, then look at that. You could almost like get rid of 80% of your layer. There was definitely a lot going on there, depending on the settings. Now, with antibiotics, yeah, we don't know if like this seemed like the range seemed a little bit smaller, but not really. In this case, the range was actually a little bit bigger, but there's not really a huge effect of the antibiotic yet when you do it simultaneously. So these are all very short-term studies. So yes, it's definitely doing something. Others out there. So this is coming from UCL. So in the UK, they used nitric oxide microbubbles to treat. This is the gram-negative Pseudomonas aeruginosa. So they made either nitric oxide bubbles or room air bubbles, and then the biofilm also originating from a wound. So they had an EBD dish which contained the biofilm. Then they added the bubbles and then insonified them, and they used a sub-inhibitory concentration of antibiotic gentamicin and placed that everything into their setup and then treated. So it's just basically 40 seconds of ultrasound at 0.9 megahertz, 500 kilopascal. And these were the direct observations they saw. So this is the biofilm beforehand, and this is afterwards. So if you don't do anything, nothing happens. But then the ultrasound in the bubbles, well, here nothing was left. And here you see a lot of red. So there's a lot of, like dead bacteria there. So there's really also something from the nitric oxide bubbles going on. So and nitric oxide is known that it can kill bacteria. So it's not just the oscillation of the bubble, but also the gas inside that is very beneficial for killing. They also quantified that, and they saw that in comparison to control, everything was significantly higher. But not really a difference whether it was room air or nitric oxide in terms of the reduction of the biofilm mass. But when they looked actually in the reduction of the culturable cells, there was a difference, because then the nitric oxide bubbles and the ultrasound were performing better than the room air ones. And for these ones, there was not, and there was also like the positive charge. So apparently the positive charge also did something to enhance the effect. Maybe they were better at hearing, so closer by. So definitely, yeah, you can treat that. Now, those are all biofilms that are grown in culture media. But if you have a biofilm in your cardiovascular system, that's not just any media. There's blood in there. So we started to collaborate with the University of Cincinnati, because they are an expert, or one of the experts, in sonothrombolysis, the solution of blood clots. And they always make their retracted human blood clots. And then we thought, okay, what if we then add the Staphylococcus aureus, and then you get this infected clot? Can we do something there? And this is what the width of the infected clot, and then the bubbles were given under flow at 120 kilohertz, and this was quite low, but this is the setting that is used for stroke. So we wanted to keep the model that they have at the University of Cincinnati the same, and they know that these settings work for their clots, and was it also working for infected clots? Now, this is one of the movies, so this is not ultra high speed, but you will see that basically there is an effect going on. It's like eating away at this clot. And if you then quantify that in the clot loss after 30 minutes of this treatment, now plasma is not doing anything. We also added a drug that dissolutes fibrin, and that we knew, the Cincinnati University, like Kirsty Holland's group, knows that you need to add that to really get clot lysis. It was a little bit all over the place, and also the antibiotic alone was all like a combination of the dissolution of the clot was all over the place. So this is not controllable. Then we started to add ultrasound, and was also not all over the place, no, not controllable. And we were so hoping that just the bubbles themselves would do something. Ultrasound and bubbles, nothing happening there. When we added to RTPA, was all over the place, but then we added a combination of also the antibiotic, and look at that. We had like a 99.9% dissolution of this infected clot. So it's definitely, very powerful combination. And you can also see that here. So this is some bright field imaging afterwards. So this is the suture that the clot is on. So this is the clot. Or I should maybe do it like this. So that's the suture. The red is the blood clot, and then the beige is the biofilm. And so that was still intact after 30 minutes of treatment with just plasma. And then look at that. When you do a combination of all, then you're left with the bare suture. So this is something we can hopefully in the future translate. That was a non-targeted bubble. So I will show you 2 examples to finish off of targeted bubbles. Now, these targeted bubbles, what can you do if it's a bacteria? Well, one of the things is use an antibiotic, vancomycin, because vancomycin actually binds to the cell wall of gram-positive bacteria. And that's what we did. Also compared it to control bubbles. And this is Staphylococcus aureus biofilm, and these biofilms were grown under flow. And then we used the confocal and the ultra high-speed imaging to also visualize what was going on. So we looked at the bubble binding. So the control bubbles are, the control bubbles are in red, and the vancomycin decorated bubbles, which target to the biofilm, are in blue. And then we started to increase the flow and just see what happens. And this is where the flow starts. And I hope you can appreciate that a lot of the red ones all wash away. So those are the control ones. You can all more easily appreciate it, hopefully, if I then separate them and then turn it on again. Yeah, so hardly any left. But these ones, okay, there were some that were leaving, but there were also a lot that were staying. Was also quantified, and the higher the shear stress, the more you lose, but definitely a difference between the two, which is good. But what about treatment? Can you do something? So here in blue is one of those target bubbles. We can also look at the oscillation. Ooh, the video is a bit weird. Here we put 5,000 cycles on because we started to notice that we need way longer bubble oscillations, because all the endothelial work was just 10 cycles, you know. This is 5,000. In the beginning, we could see the bubble. And then this is what happens. You have one black frame when the ultra-high-speed imaging is, and then here afterwards, you see this area that was created. So you can indeed, with a targeted microbubble, so this is all under flow, create an area that you can remove. And that was significantly higher than any of the controls, which you always need when you're doing imaging with a microscope, just to see that your lasers are not inducing any kind of effects. And we also do those controls also for the endothelial cells. So then, yeah, there was no significant difference between the 5,000 and the 10,000 cycles, but the range was smaller for the 10,000 cycles here. Now, because it's a targeted microbubble, you can also use it in theory for molecular imaging. So we tried that with a preclinical imaging scanner. So this is the biofilm itself, and in the contrast mode, it already has a tiny bit of signal. But then if you add your bubbles, the signal increases a lot. And to know that they're really bubbles, you can also do lines of bursts. So this is 1, 5, and 10 times of those bursts. And if you then get a black signal again, you know that indeed this signal was really a bubble. So that was all good. The bubbles could really be imaged. So maybe this can in the future be used also to diagnose the diseases better. Now, the group in Leeds also developed a microbubble that is for therapy. It could also be used for ultrasound molecular imaging, also for Staphylococcus aureus. The reason why is that this one is the meanest bug out there you can get and causes also the most mortality. And yeah, so this is why a lot of researchers going into there. They actually used an ephemer, which is a small antibody, and this was to the a protein A, so clumping factor protein A on the bacteria. And they also used an isotype control to see if that was the case, if there was a difference. And they used a microfluidic platform for their research. The setup was again optical. And this is what they saw. So there were far less control bubbles adhering than the targeted ones. So also quantified that. And what about the therapy? So this is before the ultrasound and this is after. And then you also see a lot more of those, like dead ones. And there's a shift also in where the bacteria are. So there's also some dispersion going on. And what I saw is that there's a 25% reduction in live cell count with biomass removal and an 8% also in cell death, which is also good. So that's, the summary actually of all the areas that I would like to have covered in this short talk. And for the acknowledgements, I would like to thank all the researchers who allowed me to use their data for this presentation, including the ones that are physically here. And also, this is also messed up, a lot of people that have all contributed to this research. So Department of Biomedical Engineering, where I belong to, and this is a recent picture of my group. All the other collaborators inside, like in the Netherlands, but also outside. These I didn't even get to mention all the co-authors, but these are all their affiliations. And also thanks for the funding that is making all this research possible. And of course, thank you very much for listening. There's still questions, or everyone just fed up and wants to go and have dinner. Yeah, maybe time for dinner. Yeah. So I'll be around. And, oh, yes.
I do have one about
Sure.
the direct versus indirect bubbles.
Yes.
And the homogeneity or lack thereof.
Yes.
Did this oscillation shape change as the bubbles were less homogeneous? Like, was it less spherical?
No, not that. It's not. So I also have to say that what we're doing there were not really a lot of mode shape oscillations going on. So we are currently investigating mode shapes, and specifically in relation to microstreaming, because for microstreaming you need a mode shape. And yeah, and the reason why we started to do that is because when you saw that one targeted microbubble actually in those biofilm studies removed such a large area, well, even if the microbubble it was gone, but it will have just a single path. It will not create such a large area around it. So there must be microstreaming going on. But there, yeah. So I also have to say that we're using higher pressures for the bacterial work, and then you start to see mode shape oscillations. Yeah, but for the vascular dictator, you hardly see because you're at lower pressures. I think that's the best answer. Yeah. Any other questions? I'm still around until Thursday lunch, so please don't hesitate to come and find me if you think of a question, or if you think maybe I would like to use the combined system, feel free to approach me as well. Yeah, thank you so much and have a great ISTU.
Did everything good? Like almost.
No, it was really bad.
Sorry.
So the computer crashed
Yeah.
at one point at slide 36. It decided to stop. And it was weird because there was no movie in there. It was the simplest slide. It was like a connections. It was the simplest one out there. And it just completely crashed.
Okay.
So I think that caused like a 10-15 minutes, of like, trying to get it back working again. But in the end, it did. Maxime was able to get it back up again.
Okay.
Yeah, it was so weird.
Yeah. We're sorry about that.
No, it's okay. Can happen. I mean, I was already like, oh, if I can't use my own computer, what things could go on. But it wasn't. It was really weird. And then slide 36 and 37.
Very nice presentation.
Oh, thank you so much.
And it's so interesting. We're starting with the bacteria.
So you don't.
Yeah, that was really interesting to learn more about the bacteria work. Yeah.
So
So-
much to still learn. Hi.
you